Hi, my name is Ava Weiss, and I will be presenting on electronic absorption spectroscopy of dye molecules. So to start off, the aims of this experiment is to explore the electronic absorption properties of dye molecules, as seen on the right. Specifically, we focused on the relationship between conjugated system size and energy gap between ground and excited stage, which I'll discuss in detail later. In doing so, we hope to understand how molecular size and structure influence electronic absorption properties. Additionally, we will compare different theoretical models with more complex computational models to see which gives the closest results to our experimental results. More specifically, our methods include comparing our transition energies found using absorption spectroscopy and comparing them to a particle-in-a-box, Huckel molecular orbital theory, and 4 different semi-empirical modeling methods using SciGrass. For this experiment, my hypothesis is that as the length of a conjugated chain increases, absorption energy will decrease and maximum absorption wavelength will increase. Also, as longer conjugated systems appear, it will lead to greater electron delocalization, leading to a lower required energy for electronic excitation. And out of all theoretical models employed, I believe that the Huckel molecular orbital theory will provide the best agreement with experimental data, as it accounts for molecular interactions as well as electron delocalization in conjugated systems. To provide some background, electronic excitation happens when a molecule absorbs energy, usually in the form of light, and one of its electrons gets promoted from a lower energy level, what we call the ground state, to a higher energy level, the excited state, as illustrated. The energy difference between these two states, often referred to as the energy gap, is important because it determines the wavelength of light the molecule can absorb. This is especially relevant for our experiment since we're dealing with different colored dyes. The size of the energy gap directly impacts the color we see, based on the specific wavelengths of the light those dyes absorb. So you might be wondering, why does a conjugated system matter if we're focusing on the energy gap? Here's the thing, conjugated systems, where you have alternating single and double bonds, as illustrated in the red, are key because they allow the pi electrons to spread out over multiple atoms. This makes it easier for molecules to absorb light because the energy gap between the ground and excited states becomes smaller as the conjugated length increases. Take something like butadiene, for example. Pi electrons in the alternating double bonds are delocalized across the chain. Where you have a longer conjugated system like in many dyes, molecules absorb light in the visible or near infrared range, which is why they appear colorful. On the other hand, if the conjugated system is shorter, the molecule will absorb light in the UV range, which doesn't show up as visible color. So the length of the conjugated system really influences whether a molecule absorbs light in the visible spectrum, giving it color. Here's another illustration showing the 4 dye molecules we're investigating. The boxes highlight where the conjugated system is in each molecule. As you can see, DTC has the shortest conjugated system, while DTTC has the longest. So based on my hypothesis, the length of the conjugated system should directly impact the energy gap. Since DTC has the shortest conjugation, it will have a larger energy gap and should absorb light at shorter wavelengths. On the other hand, DTTC will have the longest conjugated system, and therefore have a smaller energy gap and should absorb light at a longer wavelength. To move on to our results, after analyzing the 4 dyes, we got the following absorption spectrum. DTC had a maximum absorption wavelength of 424.7 nanometers. DTTC absorbed at 588.9 nanometers. DTDC absorbed at 653.7 nanometers. And lastly, DTCC at 761 nanometers. This shows a clear trend. As the conjugation length increases, the absorption shifts to longer wavelengths, which is exactly what we expected. Using these maximum wavelengths of absorption, we were able to calculate the experimental energy gaps for each dye. And as you can see, the second part of our hypothesis held up. The energy gap decreases as the conjugated system gets longer. This confirms that, just like predicted, a longer conjugation leads to a smaller energy gap, allowing the molecule to absorb light at longer wavelengths. To move on to our investigation of different theoretical methods, we began by implementing the particle-in-a-box method, which is a simplified way of modeling the electronic properties of molecules, especially their energy levels. In this model, we treat the conjugated system as if it were a particle confined to move within a box, as illustrated on the left. That is, it defines space determined by the length of the conjugated chain. The particles allowed energy levels are quantized, and the energy of each level depends on the length of the box or conjugated system. As the theoretical length of the conjugated system increases, the energy levels become closer together, which corresponds to a smaller energy gap. This method is useful for estimating the energy gap because it gives us a straightforward way to relate to the length of the conjugated system to the electronic energy levels. It's a good starting point, although it simplifies things a bit, as it doesn't account for all the complexities of a real molecular interaction. By applying this model to our dyes, we could calculate the theoretical energy gaps and compare them to the experimental results. This table summarizes the results we obtained using the particle-in-a-box method. As you can see, the theoretical results are very similar to our experimental findings, with an average percent error of just 0.44%. This shows that the particle-in-a-box method did a great job approximating the energy gap of the dyes, confirming that the method is fairly reliable for predicting these properties, at least within the limitations of our experimental setup. The small error further strengthens the validity of our approach and gives us confidence in accuracy of our results. The second method that we used was the Huckel molecular orbital theory, a widely used approach for estimating the electronic properties of conjugated systems. Unlike the particle-in-a-box model, which treats a conjugated chain as a simple box with a particle confined inside, Huckel theory offers a more detailed quantum mechanical perspective on the molecule's electronic structure. In Huckel theory, we focus on the pi electrons in the conjugated system and the models their interactions within a set of molecular orbitals, as pictured on the right. These orbitals are derived by solving Schrödinger's equation, assuming that only the pi orbitals contribute to bonding, while the effects of the sigma bonds are neglected. The theory uses empirical parameters to describe the interactions between neighboring atoms, with two key parameters, the column integral, which is represented by alpha, and representing the energy of an isolated atomic orbital, as well as the resonance integral, beta, which describes the interaction between adjacent pi orbitals. The major advantage of the Huckel theory is that it provides a more accurate description of the electronic structure than the particle-in-a-box model. It accounts for the interactions between atoms in the conjugated system, which allows it to predict energy levels in molecular orbitals with greater precision. When applying Huckel theory to our dyes, we relied on four key assumptions to simplify the model. All overlap integrals are set to 0, as it's reasonable to assume that the pi orbitals are perpendicular to the bonds, meaning their overlap is minimal. All resonance integrals between non-neighboring atoms are set to 0. All resonance integrals between neighboring atoms are equal and set to beta, and all column integrals are set to alpha. These assumptions allowed us to construct the necessary matrices for solving the molecular orbitals and estimating the energy gaps of the conjugated systems. For our dyes, we applied Huckel theory to estimate the molecular orbitals and corresponding energy gaps, as previously mentioned. This method gives us insight into the specific interactions between the pi electrons and can be used to predict the wavelength of light that the molecule will absorb based on the energy gap between the highest occupied molecular orbital and the lowest. By calculating the difference in coefficients between the HOMO and the LUMO, we were able to determine the theoretical energy gap. This approach resulted in an average percent error of 3.29%. To account for this error, we decided to compare the literature value of the beta coefficient with our experimental value. We did this by plotting the difference in the coefficients against the experimental energy gap. As you can see, the experimental beta value we obtained was lower than the literature value. This discrepancy suggests that the interactions between the pi electrons and our systems are weaker than those assumed in the standard model, which reflects in the smaller resonance integral we measured. This could be due to a variety of factors, such as the specific molecular environment of our dyes or the limitations of the Huckel theory in fully capturing the complexity of the conjugated systems we're studying. The difference in the beta values likely contributed to the error in the theoretical energy gaps we calculated. By comparing the experimental beta value with the literature value, we were able to refine our understanding of the system's electronic interactions and adjust our model to better reflect the true behavior of the molecules. This process helped us identify and correct for any discrepancies, improving the accuracy of our theoretical predictions. Our final investigation focused on comparing several computational modeling methods to see which one would provide the most accurate predictions for the electronic properties of our dye molecules. Specifically, we examined the following methods: MOS-MDO, MOS-AM1, MOS-RM1, and MOS-PM3. Each one of these methods is a semi-empirical approach, which means we use a combination of quantum mechanics and experimental data to estimate molecular properties. All of these methods all rely on approximations to differ in how they treat atomic interactions, orbital overlaps, and electron correlations. MNDO was one of the earlier semi-empirical methods and is known for its simplicity and speed, but it can sometimes be less accurate for complex systems. AM1 is an improvement over MDO, with a focus on providing better results for organic molecules, especially those involving conjugations. RM1 is another revision aimed at further improving accuracy by refining the treatment of electron repulsion and bonding. This method is known for being particularly good at handling systems with conjugated systems like the ones we're studying. And lastly, PM3 is the most recent method, designed to improve upon both MDO and AM1 by offering better accuracy for a wider range of molecules, particularly those with transition metals or complex bonding structures. To carry out this comparison, we created detailed molecular models of the four dyes using SciGraphs. In building these models, we made sure to accurately represent the molecular structure, carefully indicating the hybridization states of the atoms and including lone pairs where applicable. This step was crucial as the correct representation of atomic bonding, electron distribution, and lone pairs directly impacts the accuracy of the computational predictions. By ensuring these details were properly accounted for, we aim to provide the most realistic input for the various computational methods. The results of the four computational methods are shown above. As you can see, even though we analyze the same molecules, the methods, while all precise, produce slightly different results. Each method seems to have its own way of handling the molecular interactions, leading to variations in the predicted properties. In addition to recording the maximum wavelengths of absorption, we also measure the oscillator strength for each dye. The oscillator strength is an important parameter because it indicates the property of the transition between energy levels when the molecule absorbs light, essentially. It gives us an idea of how intense the absorption will be. As you can see, as the conjugated system grew larger, so did the oscillator strength. This makes sense because longer conjugated systems tend to have stronger electronic transitions, leading to more pronounced absorption peaks. Using the maximum absorption peaks shown earlier, we calculated the energy gaps and determined the percent error for each model. As you can see, among all the computational methods, RM1 produced the most accurate results. Here's a table summarizing the average percent error for each of the theoretical methods. As you can see, the particle in a box theory performed the best, followed by the Huckel theory, with the computational methods coming in afterward. So overall, here's what the results showed. The length of the conjugated chain definitely affects the electronic properties of the molecules. As the conjugated length increases, the energy gap decreases, which makes sense because a longer conjugated system means the molecule can absorb light at longer wavelengths. For example, DTTC, which had the longest conjugated chain, ended up with the lowest LTE. This is exactly what we expected. The longer the chain, the smaller the energy gap. When it comes to the methods we used, the POB method gave us the most accurate results with a minimal error of just 0.44%. As for the computational approaches, the RM1 method was the best for predicting molecular properties, giving us the most reliable data overall. Looking back at our hypothesis, the idea that increasing conjugation reduces the energy gap and shifts absorption to longer wavelengths was confirmed. However, the hypothesis that the Huckel molecular orbital theory would be the most accurate turned out to be wrong. It didn't give us the level of precision we needed, so we had to reconsider that approach. Now, when it comes to systematic errors, there are a couple of things to keep in mind. First, the model limitations. Some empirical methods can only approximate molecular interactions, so they might introduce some small biases in the results. Then there's the conjunction model itself. We simplified the system a bit, so it may not have captured every structural or environmental factor that could influence the energy gap or absorption. These simplifications are a trade-off, but they're important to consider when interpreting the results. And here are my references.